This is once again haribabuprasad in continuation to earlier discussion on digital switching. Now we will proceed with our discussion about digital switching under part 3. So in our earlier part 2, we were discussing about the concept of time switch as far as digital switching is concerned. Now we will proceed with our discussion on time switch. To start with, we will discuss about the operational modes of the time switch. A time switch can operate in two different modes. They are output associated control mode. The second one is input associated control mode. So in our earlier discussion, we have, as a matter of fact, we have discussed about the output associated control switch. Now we will continue our discussion on output associated control time switch. The switching control can be output based or input based. So as already we were discussing in part 2, taking the output associated control as an example for understanding time switch, first we will discuss about the association of the control in time switch, that is on output based. Here we will proceed with our discussion. In this mode of working, that is in output associated control mode of working, samples of incoming PCM are written cyclically in the speech memory locations in the order of time slots of incoming PCM. So the information available in the time slots are written in the buffer bar speech memory in cyclic order. So that is, the information of TS1 is written in location 1 in this location. TS2 is written in location 2 and so on up to time slot 31. If you see in this diagram, the information as depicted here is coming in time slot 4. So therefore, the information available in time slot 4 is stored in the speech memory at 4th location. This is the location. If it is time slot 1, it will be written here. If time slot 2, here. Time slot 31 means here. So this is how cyclically we write the information of the various time slots in the incoming PCM. The contents of the speech memory are read onto the outgoing PCM in the order specified in the control memory. So writing is cyclical, one after the other. But when we read the information, final ultimate goal is to transfer the information of incoming PCM to outgoing PCM. At that time, the information is read out to the outgoing PCM as per the directions of the control memory location. So here in our example, the information of TS4 in the incoming PCM is to be transferred to the time slot 6 of the outgoing PCM. So therefore, the control memory directs to read the information, to take the information from memory location 4 to the outgoing PCM time slot 6. This is how the time slot interchange takes place. We will go through the contents one after the other. Each location of the control memory is rigidly associated with the corresponding time slot of the outgoing PCM and contains the address of the time slot of incoming PCM to be connected. So each memory location, control memory location, is rigidly associated with the outgoing PCM time slots. That means here in this example, the location 6 of control memory is associated with the time slot 6 of the outgoing PCM because we are supposed to transfer the information onto time slot 6 of outgoing PCM. So here we will decide from incoming PCM from which time slot to which time slot of outgoing PCM it is to be connected so that the calling and called party can speak. We will continue our discussion on output associated control time switch. The control memory is always read cyclically in synchronism with the occurrence of the time slot. The entire process of writing and reading is repeated in every frame till the call is completed and disconnected. So it is always written, it is always read out in cyclically. So 0, 0, 0, 1 like this up to 06 then to 31. Okay. Here, since we have to send the information to time slot 6, so the information, the control memory 6 is associated with the time slot 6 of OGPCM. This directs you take the information from speech memory location 4 and send it on to time slot 6 of outgoing PCM. It may be noted that the writing in the speech memory is sequential and independent of the control memory. So here writing is sequential. It got no business with the control memory, but reading is controlled by control memory. That is, there is a sequential writing but control reading in the output associated control time switch. In case of output associated control time switch, the writing is sequential, but the reading is as per the directives of the control memory. Okay, so the same thing is mentioned here. There is a sequential writing. Here it is sequential writing, but controlled reading. So this will decide when to be read. So when time slot 6 occurs in the outgoing PCM, at the time only, the information from buffer memory is to be read on to time slot 6. Now, having understood about the output associated control time switch, we will see the second mode of operation, which is known as input associated control time switch. Now the control functionality is associated with the input or input PCM. Let us go through the contents. In the input associated control time switch, the samples of incoming PCM are written in a controlled way. That is, in the order specified by the control memory and read sequentially. So this is the basic difference between output associated control time switch and input associated control time switch. Here, while writing itself, the buffer memory location is decided. Okay, therefore, writing is controlled by the control memory. While writing into the speech memory, the information is written into the speech memory location as per the directives of the control memory. However, when we read out onto the outgoing PCM, simply it is read sequentially from 1, 2, 3, 4, 5, 6 onward, like that up to 31. So reading is cyclically, writing is controlled under the control of control memory location. Each location of control memory is rigidly associated with the corresponding time slots of the incoming PCM and contains the address of the time slot of the outgoing PCM to be connected. So here the incoming PCM time slots are rigidly associated with the control memory. This is the difference between output associated control and input associated control switch. The previous example, with the same connection objective of connecting TS4 of incoming PCM to TS6 of the outgoing PCM, may be considered for understanding. So we consider the same example. What is in our example? So the information from TS4 of incoming PCM highway is to be transferred to the outgoing PCM highway in time slot 6. That is our objective. So in case of input associated, what is the sequence of operation? The location 4 of the control memory is associated with the incoming PCM TS4. This fourth location is associated with the incoming PCM time slot 4. Hence, it should contain the address of the location where the contents of the TS4 of the incoming PCM are to be written in the speech memory. So therefore, this fourth location, since there is a mapping between TS4 of incoming PCM and the memory location, control memory location 4, there is a mapping. So this decides where the information of TS4 is to be written in the buffer bar speech memory. Of course, as you can see in the diagram, so it directs you write the information in memory location, or rather to say the speech memory location 6, so that it can be read out onto the outgoing PCM in cyclic manner. Further, we will continue. The central control writes the number of destination time slots. What is the destination time slot? Is 6, TS6, in location 4 of the control memory. So in this control memory 4th location, a reference is given to the time slot 6 of outgoing PCM. The contents of the TS4 are therefore written in location 6 of the speech memory as shown in the figure 5. So the contents of the TS4 are not written in sequential way because it already decided it should be read out onto the time slot 6. Therefore, this information available in TS4 or the binary information available in TS4, while writing itself, it will be written into time slot 6 because it is input associated control. The contents of the speech memory are read into the outgoing PCM in a sequential way. That is, location 1 is read out during TS1, location 2 is read during TS2, and so on. So as far as this example is concerned, here he has given Thus, the input PCM TS4 is switched. In this case, the contents of location 6 will appear in the outgoing PCM at TS6. So, this location information, this buffer bar speech memory contents are available when TS6 of outgoing PCM occurs. Thus, the input PCM TS4 is switched to the output PCM TS6. So, this TS4 is switched to TS6 of outgoing PCM. So, in this switch, that is in the input associated control type switch, there is a control writing but sequential reading. Here we are controlling the writing. While writing itself, we are exercising the control based on the address available in the control memory location. But reading, you read one after the other. First you read this location 1, then location 2, location 3, location 4, location 6 in our case, up to location 31. Then, having understood the concept of time switch, also the modes of operation of time switch, which we have discussed, and they are output associated control or input associated control. Now, we will try to estimate what is the switching delay as far as time switch is concerned. What is the maximum delay that may be theoretically possible, or you may construe in other words, what is the worst scenario of time delay in time switching? This we will take one with the help of an example. We will try to estimate. The writing and reading of all the time slots in a frame has to be completed within one frame time period, that is 125 microsecond, before the start of the next frame. This we all know from the basic principles of PCM. So this either writing or reading of one frame, all the time slots of one frame in case of 30 channel PCM. In 32 time slots, information has to be written or read out within a frame duration of 125 microseconds. A time slot of incoming PCM may therefore get delayed by a time period ranging from 1 time slot to 31 time slots period before being transmitted on the outgoing PCM. So the delay may range from 1 time slot duration to 31 time slot duration. 1 time slot duration means 3.9 microseconds. 31 time slot delay, that is the extreme worst condition. It can be up to 31 time slots period, that is 31 into 3.9 microseconds, which is approximately equal to 121 microseconds. How it is estimated, we will see with a practical example. For example, consider a case when TS6 of incoming PCM is to be switched to TS5 of outgoing PCM. So in this example, we are taking the worst case scenario. The information is arriving in the incoming PCM in time slot 6, that we have to send it onto the outgoing PCM in TS5, that is 1 time slot before. So how it happens? Let us see. In this case, switching can be completed in 2 consecutive frames only, that is 121 microseconds. 31 into 3.9, that is a maximum for a 32 channel PCM system. The time delay is with reference to the outgoing PCM, and it is estimated like this. So Since you have to send the information of TS6 of incoming PCM to TS5, so on the same frame, you cannot send it. You have to wait till the completion of the present frame because TS5 has already passed away as per the clock, synchronization clock. So it has to be sent the information in the next consecutive frame only. In the next frame only, TS5 appears. While reading itself, it is TS6. So TS5, when it comes, TS after TS6, you have to go up to TS31 in the existing frame. Then in the new frame, you have to wait TS0, TS1, TS2, TS3, TS4, and TS5. Then it comes. So that is 121 microseconds, rather to say 31 time slots duration. So it is estimated like this. In the frame 1, TS7 to TS31 in frame 1. That is how many time slots there are? 25 time slots duration. In the frame 1, it has to wait. In the second frame, it has to wait from TS0 to TS5. That is 6 time slots duration in frame 2. Therefore, the maximum delay is equal to 25 in the frame 1 and 6 in the frame 2. That is equal to 31 time slots duration. That is 31 into 3.9, which is approximately equal to 121 microseconds. This is the worst case scenario as far as delay in time switch is concerned. However, this delay is imperceptible to human beings. So 121 microseconds, though it is the highest possible delay, but this 121 microseconds, as far as human beings are concerned, it is imperceptible. We cannot notice the delay. We cannot feel the delay of 121 microseconds. It is in microseconds, not even milliseconds. Okay, that's what the maximum delay that can occur in time switching. Then we will discuss another aspect of time switch. This is about non-blocking feature of time switch. What is that? We will try to understand. In a time switch, there are as many memory locations in control and speech memories as there are time slots in the incoming and outgoing PCM highways. So here, before arriving at the conclusion that time switch is a non-blocking one, first we will estimate the memory locations. So we have incoming PCMs and outgoing PCMs. You have memory locations for speech as well as control. So we will estimate how many memory locations are there. Memory locations in speech and control memories is equal to number of time slots in incoming PCM highways plus number of time slots in the outgoing PCM highways. So memory locations of speech and control memories is equal to the time slots of PCM highways and the time slots of outgoing PCM highways. So here one example they have given. So assume incoming PCMs are 10 and outgoing PCMs are also 10. For example, say incoming PCMs, since they are 10, we have 320 time slots in the incoming PCMs. Similarly, outgoing PCMs are also 10. Therefore, the number of time slots in the all the 10 outgoing PCMs also 320. Therefore, there are 640 memory locations in the speech and control memory together. So if you consider both speech and control memory together, there are 640 memory locations, because in the incoming PCMs you have 320 time slots, in the outgoing also you are having 320. So totally in speech and control memory put together you have 640 memory locations. So speech bar buffering memory locations 320 and control memory locations or address memory locations another 320. Corresponding to each time slot in incoming highway, there is a definite memory location available in the speech and control memories. So for each and every time slot in the incoming highway, definitely there is a memory location available in the speech and control memory locations. Similarly, corresponding to each time slot in the outgoing highway, there is a definite memory location available in the control and speech memories. So it is so in case of outgoing PCMs also, for each and every time slot in the outgoing highways, there is a corresponding memory location or one memory location for control and speech memories. This way, corresponding to free incoming and outgoing time slots, there is always a free path available to interconnect them. To interconnect the incoming and outgoing PCM time slots, you are always having a free incoming and outgoing time slots available. So since for each time slot, there is another time slot for interconnection from incoming PCM to outgoing PCM. So there is no question of blocking. You can connect all the incoming PCM highway slots to all the outgoing PCM highway time slots. In other words, there is no blocking in time switch. So the essence of the time switch is it is a non-blocking in nature. So there is no deficiency of time slots or memory locations for switching between incoming and outgoing. Therefore, it is a non-blocking switch. Then now we will switch over to another aspect of two-dimensional switching. First, we will try to understand what is two-dimensional switching. Either space switching or time switching or single dimension switching. Suppose if you mix both time and space or vice versa, it is two-dimensional switching. Let us go through the contents of this slide. Though electronic cross points are not so expensive, the cost of accessing and selecting them, that is selecting the cross points from external pins in case of space switch becomes expensive as the switch size increases. As switch size increases, so though the electronic cross points are not expensive, rather to say they are cheaper, but the cost involved in accessing the cross points from the external pins in case of space switching becomes costly, prohibitively costly. It is expensive. Cross points, accessing the cross points is the main drawback for expanding or increasing the size of space switch. Then we will see the scenario in time switch. Similarly, the memory location requirements rapidly goes up as time switch is expanded and making it uneconomical. But in case of time switch, you do require more memory locations for expanding the time switch. So it is uneconomical as far as the requirement of memory locations are concerned. There, the accessing the cross points in space switch is a constraint for expansion. Here, the number of memory locations is a constraint for expanding time switch. Hence, it becomes necessary to employ a number of stages using small switches as building blocks to build a large network. So we will divide the large network into small building blocks. This would result the necessity of changing both the time slot, that is time switch, and highway, that is space switch, in such a network. So in a large switch, we have to adopt time slot interchange, that is represented by time switch, and highway jumping, that is taken care by space switch. So we have to mix both time slot interchange and highway jumping, or we have to use a combination of time switch and space switch. It is economical and we can expand the switch. Hence, the network usually employs both types of switches. So we use space switch and time switch, and therefore it is known as two-dimensional switch. Since we are deploying both space switch stage and time switch stage, so we call the network as a two-dimensional network, space dimension and time dimension. These networks can have various combinations of two types of switches and are denoted by the various combinations of time and space. It can be TS, that is time stage and space stage, or you can have space stage, time stage, and space stage. Okay, two-dimensional. One space dimension, other one is time dimension. Of course, space stage two times, that is in the input, in the output, in between, that is time stage. Here another example, TST. In the input you have time switch, in the output also you have time switch. In between sandwich is space switch. And you can have something like this also, TSST. Here input is time, output also time. In between there are two space stages. So this is all in nutshell about two-dimensional switching. Further we will discuss on the same concept of two-dimensional switching. To ensure full availability, it may be desirable to use only time stages. So as we already understood, there is no blocking in time. So to ensure full availability, it is desirable to use only time stages. However, the networks having the architecture like time, 3Ts, time stage, and another example, 4Ts, that is time stage, etc., are uneconomical, considering the acceptability of tolerable limits of switching delay in a practical network. So earlier we have discussed what is the worst scenario of delay in time switch. For one time switch, the maximum possible delay or worst scenario is 121 microseconds. Suppose if you have 4 Ts, then to increase the size of the switch, suppose you are having a 4-stage time switch, all 4 stages are time switches only. So the worst scenario can be 121 into 4. So much of delay will be there, that is 484 microseconds. So perhaps it may be something nearer to the human perception. So we avoid such modularity in practical network. Similarly, a two-stage, two-dimensional network, TS or ST, Two-dimensional, two-stage means it can be TS or it can be ST. Input to time, output to space. Input to space, output time is basically suitable for very low capacity networks. So we can deploy like TS bar ST model, but they cannot take care of more capacity networks, high traffic networks. So they are used for low capacity networks like private branch exchanges, PBX, popularly known as PBX. The most commonly used architecture has three stages. So generally in practical networks, we prefer three-stage networks. It may be STS or TST for high capacity network. So the most preferred the preferred network may have three stages with architecture like STS, space, time, space, or it can be time, space, time for high capacity network. However, in certain cases, their derivatives like T, SST, double ST, T double ST, T triple ST, etc. may also be used. So, apart from STS or TST, their derivatives, the examples they have given. So, input time, output also time. In between, you have two space stages. Here in this example, input time, output also time. In between, you have three space stages can also be used. Once further, we will continue our discussion on two-dimensional switching. Now, we are trying to understand which is better, STS or TST. An STS network has relatively simpler control requirements and hence is still being favored for low capacity networks bar exchanges. So STS advantage is simpler control requirements, but it got its own limitation about taking care of high capacity networks. So we deploy STS type networks because of its simpler control requirements in low capacity networks, smaller exchanges. As the blocking depends mainly on the outer stages, which are space stages in STS networks, it becomes unsuitable for high capacity systems. So why this STS is not suitable for high capacity systems is given here. Blocking depends mainly on the outer stages. So outer stages are in STS space stage, space in between time. So it is therefore it is unviable for high capacity systems because of the blocking feature. So space switching is having the drawback of blocking. It is not non-blocking like time switch. So this is less preferred for high capacity systems. Only for low capacity systems it is preferred because of its simpler control requirements. A TST network has lesser blocking constraints as the outer stages are time stages which are essentially non-blocking and the space stage is relatively smaller. If you consider TST network, the input is time stage, output is time stage, in between sandwiched is space stage. Since the input as well as the output are having non-blocking switches, so the TST presents lesser constraints as far as blocking is concerned. Okay, therefore TST is the most cost effective for networks handling high traffic. So if you compare between STS and TST, so TST is the most cost effective for networks handling high traffic because of its non-blocking feature in the input as well as in the outputs, and because of the minimizing of space stage. Further, we will continue our discussion on two-dimensional switching. However, for still higher traffic handling capacity networks like tandem exchanges, it may be desirable to use TSST or TSST architecture. So in case of tandem exchanges, it has to handle very high traffic. So perhaps TST may not be sufficient to handle that much capacity. So we use the architecture like TSST. That means the input you are having time stage, output also the time stage. That is non-blocking type. In between you are having simpler control requirements space stages of two, but they are blocking type. Technically speaking, they are blocking nature. So we sandwich the space stages, maybe two or three, like in this example, between the input and output time stages. So this type of architecture we prefer in case of tandem exchanges. Nowadays we are calling as trunk automatic exchanges with reference to our STD, we can say. The choice of a particular architecture is dependent on the other factors also, and they are enumerated below. So the actual architecture, what is the architecture we have to select depends upon about the technicalities of time and space stages, or the time stage in the input and output and space stage input, and also some more factors are given below. Implementation complexity. We have to see the implementation, the complexity involved the implementation, modularity. So we have to subdivide the network into different modules. Then testability. So for testing of the network or testing of the lines should also be taken into consideration what is the architecture we have to follow. Then expandability. In future, say you are installing, say, some 6,000 line sections. Tomorrow you may have to expand it to 10,000 or 20,000, depending upon the increase of the subscriber base. So whether the architecture, whatever we are adopting, is suitable for expandability or not also, we have to take into consideration before deciding the architecture of the switching network. As a large number of factors favor TST structure, therefore, it is the most widely used structure. So in spite of all these things, so many factors, they suggest it is better to have TST structure. So most of the our factors, governing factors, they favor TST. Therefore, TST is the most widely used architecture. Then we will discuss in our next part about the TST architecture, which is widely used. So if you like my video, please subscribe to my channel and also give some encouraging comment. Thank you.